Okay, so can you guys see my screen now?
Yes, sir.
Yes, sir.
Yes po.
Yes, sir.
Any other answer regarding with exercise number 1? Or did you guys get the same answer?
Yeah, the same.
All right then. So is there anyone who wasn't able to get the same answer so that we can explain this one? Or I can show you guys the solution. All right, so I
Pwede
guess,
sir pa-show ng solution, sir.
all right, so you want to see the solution. Okay, so wait a second. All right, so from here, as you guys can see, oops, you have here the value of your R1. R1 is 3.4, 3.4, okay, ohms. And then R2 is missing, and then R3 is 6.2 ohms. Okay, and then we have a current that is flowing. Where is that? 1.5 amps. So our letter I is equal to 1.5 amps. And then your voltage source is 24 volts. So V is equal to 24 volts. All right, so from there, you can actually come up again with an expression wherein R total is equal to R1, R2, and R3. R1 plus R2 plus R3. And then as you can see, we have two missing values, which is the RT and then the R2. Okay? So we have to solve for the RT first. Okay. So for us to be able to get the RT, so just take a look on our given values. So for the RT, we have the I V times divided. This is correct. V divided by I. V divided by I. Okay. So as you guys can see, we have this voltage source, which is already given, and then we have the I, which is again already given. So from there, you can already solve for the RT. So V is 24 volts, and then I is 1.5 amps. So from there, you can solve this one using your calculator, of course. 4 divided by 1.5, you'll get 16 ohms. So this is our total resistance in this circuit. Okay. So from there, you can now use this expression since there's now only one missing variable. Okay. So let me just change this expression. So the one that we're looking for is R2. So R2 is equal to RT minus R1 minus R3. So just transfer those other variables. Okay. So RT is 16 ohms minus R1. R1 is 3.4. 3.4 ohms. And then R3 is 6.2 ohms. So from there, we should get 6.4 ohms. So were you guys able to follow my solution?
Yes, sir. Thank you po.
Yes, sir.
Yes, sir.
Okay then. So the answer for your R2 is 6.4 ohms. All right, so let us now proceed to the electric power. Okay, so when the electric power or power, it is the rate at which work is done. Okay, if there is a work that is being done, we call that one power. Okay, and in the mechanical system is then that expressed in horse power. Okay, so as you guys may all know, horsepower is equivalent to a rate of 33,000 foot-pounds of work per minute. Okay, so where did this foot-pounds came from? It actually came from a real horse, and as you guys can see, 1 horsepower is equivalent to 33,000 foot-pounds per minute. So meaning, 1 horsepower, and then in 1 minute he can, for this horse, can lift this one. Medyo magulo. But this horse can lift this one 33,000 pounds in 1 minute. So medyo magulo or it's quite confusing, but this is where it came from. I actually wasn't able to see the actual footage on how did they measure this 33,000 foot-pounds. But just imagine that this one is 33,000 pounds, and then maybe this horse is, lifting this one for 1 minute. And then they've considered that one as a measurement of 1 horsepower. Okay. So that's how did they come up with HP or horsepower in our car, in our motorcycle, etc. etc. So this one came from, of course, not only with a specific horse. This one came from an average size of adult horse. Okay. So of course, some horses are, say, stronger than the other horse. So some maybe might be able to lift 34,000 pounds. Some might be able to lift maybe 30,000 only. So it's not consistent. We're going to measure them one by one. But in here, they've got the average, okay, horsepower of an adult horse. Okay. So that's how they come up with 1 HP is equal to 33,000 foot-pounds of work per minute. So this unit was actually originated by James Watt. So this is Mr. James Watt, who have come up with such idea wherein why not we develop a unit called horsepower with the use of real horses to measure such power. Okay, so in year 1782, he found it is necessary to specify how much power his new steam engines would develop in terms of the horse push a crank as they walk in a 24 feet diameter circle. Okay, so this is not just by simply lifting a certain thing. So this one is also uh, inside a 24 feet diameter circle. Okay, so it's not straight line, but they are in a circle. Okay, so let's just keep on uh, pushing or maybe pulling a crank or whatever is that they're pulling, and then he was able to measure that 1 horsepower is 33,000 foot-pounds. All right. So are we clear with this one so far?
Yes, sir.
Yes, sir.
Okay. So I would like you guys to explore more on how did they really measure this 33,000 foot-pounds. Okay, now I'm curious, but before I'm only worried about, okay, 1 HP is equal to 33,000 and so on and so forth. I didn't search more. How did they come up with 33,000? Okay, and then such conditions. All right, anyway, so that's the history when it comes to horsepower. And since we're talking about electric power, it's not just a simple power, okay? So they adapted the idea of Mr. James Watt, okay, and then applied it into wattage, okay? So as you guys can see right here, 1 HP is equal to 745.7 watts, or approximately 746 watts. So again, how did they come up with such thing? So since the average force was assumed to exert a force of about 175 pounds and made 2.5 complete revolutions per minute, it followed that 1 HP has an equivalent to 175 times 24 times pi. So this 24 times pi is the circumference, okay, of that circle. So 24 in diameter. So you guys can see right here, 24 in diameter, and multiply to get the circumference times 2.5, okay, which is the revolutions per minute. And from there, he was able to solve this one, 33,000 foot-pounds per minute. All right. So that's how they've come up. So again, they've used average force, so all adult force, and then they've measured on how they exert certain force, wherein they figured out that each or an average force can exert a force of 175 pounds. And then in a certain condition, they were able to come up with this formula. So 2.5 revolutions, and then this, or the diameter of that horse, keeps on running. So he was able to get 33,000 foot-pounds per minute. So later on, when the unit of electrical power was adopted, it was designated the watt in honor of the inventor James Watt. Right? So that's the history of the unit of our power. So when we say power, watt. Okay. So that's the unit of this power. Came from James Watt. Right? Oops. So yeah, so moving on. So we have here the fundamental definition of power. So when we say, again, power, it is the rate at which work is done, or the rate at which electrical energy is transferred to a circuit, or the time rate of doing a certain work. Okay. So we have another unit here wherein we call that 1 joule per second. So the unit of electrical power is defined in terms of the joule per second. So the latter being the work done when 1 coulomb of electricity is moved through a potential difference of 1 volt in 1 second. So from there, they were able to come up with a formula wherein 1 watt, okay, is equal to 1 joules per second. Okay, and then for you to be able to solve for the power, okay, which is in terms of Ohm's law, so we have here E times I, wherein E is your voltage source, and then I is for the current or the ampere. All right. So again, 1 watt is equal to 1 joule per second. Right? So just memorize this one. P is equal to E times I, because you can come up with a lot of solutions. Same with Ohm's law, which is I equal to B divided by R. But in power, so we have PEI, or P is equal to E times I. And then again, since E is equal to IR, so this one is actually the Ohm's law. V is equal to IR, or E is equal to IR, so they are just the same. P may be written in terms of I and R dash. So just simply substitute the E by IR. So yeah, let's say E is not given, but your I and then your R is given, then you can use this formula instead. So as you guys can see, we have IR times I. And then if you're going to simplify this one a little bit more, then you will get this formula, I squared times R. So were you guys able to follow so far, and how did we come up with such formula? Hello guys.
Yes, sir. Yes, sir.
Yes, sir.
Okay, so one more thing that I forgot to mention. So since 1 watt is equal to 1 joule per second, so the reading of this one is 1:1. So if you have 200 watts for your computer, then this one is 200 joules per second. If you have this 1,200 watts, so in joules we have 1,200 joules per second. Okay, etc., etc. But mostly the one that we're always using when it comes to power is watt. Okay, but in other maybe other countries, maybe they're using joules per second. All right, and again, this P is the same with this I squared times R, or this E times I. So they are just equal with each other. They are derived from Ohm's law. So you can also have this equation wherein instead of substituting the value of your E into IR, so you can also substitute the value of your I into V divided by R, okay, or E divided by R. So from there, as you guys can see, it will form this equation. So E times E is E squared divided by R. Okay, so were you guys able to follow on how did we come up with this another
Yes, sir.
formula? All right then. Okay, so as long as you know the fundamentals, okay, or the basic formulas, then you're good to go. Okay, so we have here the electrical power conversion. So again, as I mentioned a while ago, 1 HP is equal to 746 watts. So electrical power is frequently converted to mechanical power, especially nowadays that we are now into mechanical or electrical power. So we are not in, a manual labor or manual energy or force anymore. So we are now into mechanical things. So we let the mechanical uh, devices to lift that for us. So for example, in the case of electronic or electric motor, so precise relationship is therefore required between the mechanical and electrical equivalence of power. So meaning this mechanical needs electrical power for it to power up this one. So again, in powering up, let's say you need 4 horsepower of electric motor, since maybe the one that it's getting it's quite heavy, let's say an elevator, so I'm not really sure, but let's just assume that you need 4 horsepower. Maybe that one is not strong enough to withstand the elevator. Anyway, we'll just use 4 horsepower. So if you need 4 horsepower, just multiply this one by 4 also. So 4 times 746 watts, then you'll get roughly 3,000, 3,182, I guess. So you need at least 3,182 watts for you to power up such mechanical thing. Okay. So the higher the horsepower, the more energy or the more electricity that he needs to consume on that thing. Okay. So imagine 1 horsepower is already 746 watts. What if it's 100 horsepower? What if it's 200 horsepower? Okay. So it needs a very high usage of wattage. All right. So in reality or in our society, we don't actually use watts only. Okay, if the Beneco or if the call this one Meralco, yeah, Meralco is for Manila. Let's say they're not going to measure your wattage usage in your home, so we don't use watts, but we use kilowatts. Okay, so in that case, you have to convert this 1:1 into 1,000:1 kilowatt. So 1 kilo is equivalent to 1,000. All right. So the same with this one, you can actually have 1 kilo, but we don't really use that one in horsepower. It's still horsepower. Okay. So in watts, we can say 1 kilowatt, but in horsepower, we don't say 1 kilo horsepower. Okay. There is no such thing actually. So in here, we have 1,000 horsepower is equal to 1 kilowatt. Okay. So as you guys can see right here, they are not actually 1:1. So sorry for that. It's not 1,000 horsepower is equal to 1 kilowatt, but 1 horsepower is equal to 746 watts. So if we have 1 kilowatt, we have here roughly 3/4 of that horsepower, like 0.75. Okay, so you can just round up this one. So 746 into 75, okay, or 750, wherein you will get exactly 3/4 kilowatts of that one. Right? All right then. So let's have this example number 3. So a building load consists of 30 100 watt, and then 50 75 watt, and 40 60 watt incandescent lamps. So all of them are lamps that with a different wattage. Okay, and then all connected in parallel to a 116 voltage source. So we have two questions. Calculate the total power. For letter B, the total current. And for the letter C, the current through each size of lump. So as you guys can see right here, we already have the solution. So calculate the total power. So this one is the simplest one, since all you need to do is, get the summation of your P sub 100, which is the 100 watts, and then P sub 75, which is the 75 watts, and then P sub 60, which is the 60 watts, right here. And then since they are not only one, so we have to multiply them by their numbers. So here we have 30 times 100 watts, so just solve that one, and so on and so forth, and then just add all of them. Okay, so 3000 plus 3750 plus 2400 is equal to 9150 watts. So that's how we come up with the result of this one. So were you guys able to get the result of this one? 9150 watts.
Yes, sir.
Yes,
Yes?
sir.
Yes, sir.
Okay then. And then when it comes to total current, okay, as long as you know the total resistance and then the total voltage, then you're good to go. Okay. But since we don't have the resistance in here, but we can still solve for the current using the power. As you guys can see, we have the power here, and then we have the voltage source. So from there, we can already solve your current. Okay, so as you guys can see, we have the power, which is 9150 watts. So just put that one here and then divide it to voltage source, which is 116 uh, voltage source or volts. So from there, just put this one to your calculator, then you will get 78.9 amps. All right. So are we clear with letter B, total current?
Yes, sir.
All right then. So the last one here is the current through each size of lamp. So as you guys can see right here, you need to get the individual current on each node. Let's say node A, node B, and then node C. So they are connected in parallel. So you have to get the individual amperes. Okay. So of course, when we say individual currents, we also need to get the individual power. Okay. So we have here the individual power of P sub 100, individual power of P 75, and then individual power of P sub 60. Okay. So from there, you can still use this formula. I is equal to P divided by I. Okay. But with their individual corresponding variables. So for the P sub 100, so we have here 3000 divided by 30, which is the, where is this one? Sorry. This one is the whole, okay? This one is the whole. So you have to get one lamp only, okay? So each size of lamp. So you have to divide it by its count. Since we have 30 counts, so you have to divide it by 30. Okay, so 3000 divided by 30, so it will lead you back to 100. So the same with this one. So it will lead you back to 75 and then 60. Okay, which is already given. So P sub 100, P sub 60, and so on and so forth. So from there, just multiply all of those with our voltage source, which is 116. Then you will get their individual current, okay, on each size of lamp. So for P sub 100, one lamp is consuming 0.863 amps. And then for 75 watts, it is consuming 0.646 amps. And then for 60 watts, it is consuming 0.518 amps. So as you guys can see, they are also proportional with each other. The higher the wattage, the higher the current. The lower the wattage, the lower the current. Right? So are we clear with this one so far?
Yes, sir.
Yes, sir.
Yes, sir.
So actually you can revise this one. Instead of using 3000, just use 100 divided by 116. 75 divided by 116. 60 but divided by 116, then you will get the same answers. Right? Okay, then, so let's move on to the next example. So example number 4, using the data from example number 3, which is this one. Calculate the equivalent resistance of the entire load. Okay, and then for letter B, the resistance of each size of lump. Okay, so when we say equivalent resistance, we are now getting here the total resistance of that circuit. Okay, so you can still use the formula, okay, but it would be, so we have here Rx is equal to E divided by I. Where is that one? Are we able to define E divided by I? Anyway, so it also came from here, E divided by I. Wait, I think we wasn't able to define this formula. Let me just look into that one. R is equal to E divided by I. Okay, so I think we wasn't able to define that one. Anyway, so we have this formula, P is equal to E times I, right? So we need the resistance, which is E is equal to I times R. So from here, we can replace this E into I R, which will be multiplied to this I. So in that case, we'll get I squared times R. And then the one that we're looking for is the value of your R. So just transpose this one below. So R is equal to P divided by I squared. Okay, so we have this new formula, which I wasn't able to include in here. So that is R is equal to P divided by I squared. P divided by I squared. So we
Yeah, I
already have,
think, yeah, it's there. So we can also use the first one, which is V equals to I how. So how equals to E over I.
I see. So sorry, I was actually into the usage of the power. Okay, for in this example, we don't actually have a power. Okay, so we have the resistance, the E, and then the I. So this one is basically just Ohm's law. Okay, so again in Ohm's law, we have the V is equal to I times R. So if you want to get the R, so R is equal to V divided by I. Am I correct? V divided by I. So E is the same with V, and then your I sub V is equal to I. All right, so from here, your voltage source is already given, which is 116 volts. So you guys can see right here. and your ISFP or total current is already solved from letter B, which is 78.9 amps. So just put it right here, and then you will get 1.47 ohms as your total resistance. So you can use this formula, this Ohm's law, and then our newly defined formula, which is the where is that one? R is equal to pi squared. Am I correct? Yeah, R is equal to P divided by I squared, which is this one. All right. So either of those two, you will get the same answer, which is 1.47 ohms. Okay. So if voltage source is missing, then you can use this one. But if we have the voltage source, then you can use this Ohm's law. And then for the last one, the resistance of each size of lamp. So again, you can just simply use the R sub 100, R sub 75, and then R sub 60. Okay, so from our past example, R sub 100 has an equivalent of amps of 0.863, and then R 75 is equal to 0.646, and then the last one is 0.518. So from there, you can already get the total resistance of each size of lamp. Right? So R is equal to V divided by I, which is this one. So were you guys able to follow so far?
Yes, sir.
All right. Okay, so I didn't show you guys on how did we get this one since it's already in here. Okay, so just look for the values. Okay, since it says here, so one came from example number 3. So if your answer in example number 3 is correct, then your answer in here is also correct. All right, so last one is example number 5. So why did I say last? Since we don't have enough time anymore. Okay, so we will just continue the rest next meeting. So example number 5, an electric motor drives a mechanical load taking 18.8 amps from a voltage source of 230. So we have two questions. Calculate the power input to the motor. So power. And then letter B, calculate the horsepower output if it operates at an efficiency of 86.4%. Okay, so here first, we have the power. So the given variables are the I and then the voltage source. So from there, we can just simply use the formula P is equal to E times I. Simple as it is. So your E is 230, your I is 18.8. So from there, you will get 4,320 watts. So that's the needed power if we have those kind of inputs. And then for the last one, horsepower output or the P out if it operates at an efficiency of 86.4. So as you guys can see, we already have here the total power, okay? And it's only asking us the 86.4 percentage. Oops, what is that? 86.4 percentage of that power. So just multiply this 4,320 by 0.864. So from here, you are now getting the 86.4% of that power. So in here, it's asking us the horsepower. So we have to divide this one by 746 horsepower, okay, for us to get a unit of 5 HP. All right.
So we divide by 746 horsepower or 746 watts.
746. Okay, so actually the exact value is 745.7 came from here, but we just round up this one. So instead of 0.7, we just split that one, so 74 6 or 746 watts. Okay.
Okay.
So do not use the 745.7. Just use 746. Okay. All right. So yeah, that's it for today. So we will just continue the rest next meeting. So just stay tuned on my announcement since I'm still creating your quizzes and your practice activities. Right. So thank you guys for coming and see you guys
Thank you,
next
sir.
time.
Thank